Good day, chemistry fans. We're doing a new formula in this part, and having seen this, I realized I've used this a couple of times already. So you probably saw me do something with 1 times 10 to the minus 14 and wondered where it came from. I apologize for that. The thing that we're using, this is a useful little tool, is that there's an equilibrium constant for H3O and OH. And it turns out for any water at room temperature, the H3O concentration times the OH concentration comes out to 1 times 10 to the minus 14. We knew already that when a solution is more acidic, it's less basic at the same time, and this mathematically explains why. The bigger one of these numbers is, the lower the other number must have to be. And if you're comfortable with logarithms, you might be able to explain to yourself why this formula tells us about how come 14 is the total of a pH and a pOH. That 14 is lurking here, and if you did some logarithms, maybe with negative signs on them, you might find you can explain why the combination of these two numbers has to add up to 14. I'll leave that for the math nerds among you. So, if we have H3O concentration, or if we're looking for an H3O concentration, sorry, and we know the hydroxide, if we know that H3O, I just erased this, bad planning, equals 1 times 10 to the minus 14, which we call Kw, the water constant. If you want to solve for H3O, you divide both sides of this by OH, and you get H3O plus equals 1 times 10 to the minus 14 divided by OH. If we were looking for OH, we would divide both sides by H3O. So either way, it's the ion you want to find equals 1 times 10 to the minus 14 divided by the ion you already know. So in this case, if we do 1 times 10 to the minus 14 divided by 2.45 times 10 to the minus 4 for the hydroxide concentration, locate calculator, turn on calculator, 2.45 times 10 to the negative 4, I get 4.08 times 10 to the minus 11 moles per liter. This has three significant digits. The ion product for water is actually 1.00, so you're okay to three significant digits for that. That number's in the data book if you ever want to look it up. And that's it. That tells us this solution, which had a fairly high hydroxide concentration, has a fairly low H3O concentration to go with it, so definitely basic. Here again, if they give us hydroxide, we want H3O. Our H3O, the ion we want to find, is the ion product for water divided by, and our hydroxide is 2.5. 1 times 10 to the minus 14 divided by 2.5 comes out to 4 times 10 to the minus 15, and with 3 sig digs, that should be 4.00. And here they have us go the other way. They ask us for the hydroxide concentration, but the formula still works the same way. The hydroxide concentration will be the ion product for water. Do the sig digs right this time. And our H3O is 3.65, so divide by that. This is a really high hydroxide concentration, very acidic, so I expect to get a super low value for the hydroxide. Lots of acid means minimal base. Divided by 3.65, and I get 2.74 when I round it to 3 sig digs times 10 to the minus 15 moles per liter of hydroxide ion. Not too bad, I hope.